Hello, and welcome to today's live session, Introduction to Pressure Sewer Systems. I'm Rachel Seiler, today's host and Marketing Communications Manager for E1. Before we get started, some housekeeping notes. All attendee lines have been muted. We'll be recording today's session, and an archived edition will be available on E1's website. Upon successful completion of today's webinar, you'll receive a PDF of the presentation as well as a certificate of attendance. And finally, we'd love to hear from you. We've allotted about 15 minutes of Q&A during today's session, so please make use of that and the chat feature. If we don't get to all your questions, we'll answer them in a follow-up email. So now, without further delay, I'd like to introduce today's presenter, Chris Nedwick, Eastern Regional Sales Manager for E1. Chris has more than 10 years of experience in both wastewater sales and field service and has guided many municipalities through successful pressure sewer projects. Chris, take it away.
Hi, Rachel, and thank you. Can you hear me okay?
I can, thank you.
Thank you. Thank you, and thank you one and all for joining us today. Our webinar is Introduction to Pressure Sewer Systems. We really appreciate you taking the time to take part. And as Rachel said, we really do encourage your questions at the end, so we do hope to hear from you. E1 low pressure sewer systems offer the designer new freedom in solving wastewater challenges that have defied reasonably economical solutions. Each low pressure sewer design should be considered on the basis of its own unique circumstances. On such a basis, a sound choice between gravity and low pressure sewer systems can be made. General criteria aid the engineer in making a preliminary choice between several alternative systems: entirely low pressure, entirely vacuum, entirely gravity, or a combination. In this presentation, these criteria are presented and intended to serve as a general guide. The final decision and design are the responsibility of the project consulting engineer, whose knowledge of local conditions, including construction costs, regulatory requirements, and the client's particular needs become vital to the preparation of the final designs and specifications. Low pressure sewer systems have low initial front-end costs compared to gravity systems, which have nearly all of the total investment allocated in the first stage. With low pressure sewer, grinder pump costs are incurred only as construction progresses. These costs will be deferred for many years in certain types of development programs. A low pressure sewer system is not subject to I&I from groundwater or from surface stormwater entering through a leaking pipe joint or manholes. With zero infiltration, treatment plants need not be sized to handle peak flow rates caused by infiltration. Treatment efficiencies can be more consistent and treatment plant operating costs decrease. For builders, E1 low pressure sewer systems may become critical in determining whether marginal lands can be economically developed. Many attractive sites have been considered unsuitable for development because of excessive costs related to conventional sewer systems, such as sites with hilly terrain, land with negligible slope, high water tables, poor percolation, rock, seasonal occupancy, or low density. Many municipalities are planning to convert from septic tanks to central sewage collection and treatment systems to minimize health standards and environmental deterioration. Surface restoration costs are similarly minimized. Sewage delivered to the treatment plant, because it contains no infiltration, is more uniform in strength, the volume is smaller, and peaks are greatly reduced. In this presentation, we will evaluate low pressure sewer, LPS, gravity, and vacuum. So now I'd like to transition to myths and misconceptions. Again, myths and misconceptions. Gravity sewers, once they are installed, gravity sewers are free. And certainly everyone on this webinar, I trust, knows by now that gravity systems certainly are not free. No regular maintenance is required. Again, myths and misconceptions. No cost is associated with transporting and treating inflow and infiltration. With vacuum sewers, myths and misconceptions. It's a sealed system with no infiltration. It's simple to operate and to troubleshoot. And multiple homes can share a vacuum valve chamber. Again, myths. Pressure sewer systems. One of the most frequent bits of feedback when it comes to myths and misconceptions that we've heard over the course of the years is that it requires constant maintenance. And this is certainly not the case, or that it's expensive to operate. And there are ample slides and information in this presentation which show that that's not true. So when we're having discussions with potential stakeholders about where to use pressure sewers, these questions typically come up. Where is this system or this technology going to deliver the most value? And the answer is, in most applications. This is no longer an alternative technology. It is a mainstream technology. It's a suitable technology. And the answer is really wherever the terrain is undulating or hilly, wherever rocky soil conditions exist, and where there's high groundwater table. We know from speaking with stakeholders and end users that dewatering costs and regulations are higher and more stringent than they ever have been. Pressure sewer, because it's minimally invasive, can help eliminate those costs by eliminating or reducing open trench techniques. Where the terrain is flat, and also in conjunction with existing sewage collection systems to expand sometimes existing service areas. And why is pressure sewer used? Well, it's a small diameter network which follows the contour of the landscape. Solids are macerated, allowing small diameter pipes, usually between 2 and 4 inches, to be utilized. Wastewater can be pumped. It's pumped downhill, uphill, around things. There's no pipe slope required. Pumping uphill and downhill with shallow installation becomes feasible. The network is fully sealed. It's resistant to stormwater infiltration. It's a simple installation, relatively speaking. Again, horizontal directional drilling is often utilized, and it requires no critical slope to work. Pump systems with positive pressure are common and more intuitive than vacuum or negative pressure systems. Therefore, technicians are more successful in diagnosing and correcting faults. Again, more intuitive system. Grinder pump stations provide a level of emergency storage in the event of a power outage or equipment fault. Grinder pumps and low pressure sewer systems actively process solids and debris with a grinder, unlike vacuum systems, which use only the force from differential air pressure to move wastewater. E1 low pressure sewer does not have any central critical infrastructure to operate. A fault at one site will not affect the operation at other sites. This allows for quick restoration under certain conditions. Low pressure sewer can identify system abusers, debris, or infiltration more effectively than vacuum or gravity systems. Low pressure sewer systems have virtually zero stormwater infiltration, as mentioned, which significantly reduces the burden on downstream infrastructure and makes the entire system more predictable. So, in speaking with mainly engineers and more technical folks, we get a lot of questions about discharge locations. A lot of times they may be dealing with an application where there is some existing infrastructure that they need to interface with, or they're just trying to understand various design options. So where can a E1 progressing cavity system discharge into reliably? And the answer is in most locations, as long as we can overcome force main pressure. We're going to get into hydraulics and pump design in further detail in this presentation, but you'll see, and I'll just mention now, we can go up to 185 feet of total dynamic head, and we can go down to a negative head and still operate reliably and predictably. So the result of that is where there's an existing gravity manhole, where there's a gravity main. Again, these are locations where we can discharge to. Maybe it's an existing wastewater treatment plant, the headworks at a treatment plant, a lift station wet well. If it's in a neighborhood, maybe there's some existing gravity and someone's trying to tie into that existing system. We can go right into that wet well. Where there's an existing force main, pressure sewer or larger municipal force main, that is. Sometimes even septic tanks or communal septic systems as well. Treatment lagoons. Yeah, if an appropriate technology, we can certainly interface well with treatment lagoons. On-site treatment systems. Larger or intermediate grinder pump stations, and these can be E1 stations or other types as well. And even there are some documented cases of vacuum systems being integrated with E1 systems or vice versa. We are a solutions provider a systems and solutions provider at Environment One. We make an appliance pump that is designed specifically for the application. The basic design of our pump has been tested over the course of 5+ decades. Again, purpose-built for the application. Everything that we do at Environment One is focused on keeping operation and maintenance costs as low as possible and customer satisfaction as high as possible. And one of the things that is very central to our philosophy is our equipment is interchangeable. It is modular and it is interchangeable, and it does not require various parts from various different types of pumps. Consistent and predictable flow from a hydraulic standpoint. One of the metaphors that we often use is, you're going to have varying system pressure in any low pressure sewer system. So you're going to want to have a pump that will operate predictably at 5 psi at one part of town and 25 psi or 35 or even higher at another part of town. So consistent and predictable flow. We'll talk more about that in the hydraulics section. Low inlet velocity prevent clogging. This is also very important to the design. Again, our pumps don't require any preventative maintenance whatsoever. So it's critical that our grinder design operate with low inlet velocity and does not clog, which it does not do. Simplicity of repair and/or replacement. Our assets are designed and intended to be troubleshooted and fixed on location. And design assistance is critical to everything that we do. If you're considering working with any low pressure sewer provider, make sure that you're going to want to make sure that design assistance is front and center and is something that's provided by that manufacturer. We'll talk more about that. So one of the things that we do is we offer design assistance. So we offer layouts to be served by grinder pumps. So we're going to require some basic information from folks, and we're going to want to know, what is the size of the system, how many connections are there, what part of town is this serving, what are the potential flows per connection or lot. Typically, we see 200 gallons per day utilized in the United States for that figure. We're going to want to know what the pipe type is that might be preferred by local regulation or code. Typically, it's Schedule 40 as long as it's pressure rated. SDR 26, SDR 11, SDR 21. These are some of the more common, typically between 160 and 200 PSI rated. We're going to want to have an understanding of the topographical characteristics of the application. A lot of times Google Earth is used, but certainly other sources as well. Where are the discharge locations or the end of the pressure sewer system, and what is it pumping into? Again, these are just typical things that we're looking for upfront to provide an application engineering study for the engineer typically. Where is it located from a climate perspective? What is that minimum frost depth going to be? And what are the code requirements locally that might have to be taken into consideration? And also any other relevant information regarding geographies, flow, site conditions, or special requirements. System piping, we mentioned some of the materials that are used, but usually HDPE pipe is what's utilized, certainly in this day and age. And again, we do see PVC style pipes used. These are usually sourced locally. And again, some of the local codes and regulations and preferences are going to drive decisions related to what type of pipe is used and also what's readily available in that market. Air release valves are typically required with an E1 system. We're going to call for these to be integrated at intervals of 2,000 to 2,500 linear feet, or on horizontal runs that lack a clearly defined high point. Really, where there's any high point or major downhill runs, it's a sound engineering practice to include these in key locations, and we're going to work with you hand in hand to point out where those locations are going to be. One of the things that we also look at as part of this ongoing dialogue with end users and stakeholders about when to utilize pressure sewer is life cycle cost analysis. This is something that, to my knowledge, we're the only organization out there that does this, in comparing different types of collection methods and costs related to those methods. But what it is an economic analysis that utilizes engineering and financial inputs to compare alternatives. So typically we're going to look at gravity, vacuum, and low pressure sewer. And this is a non-biased, black and white view of what the costs are going to be based on local conditions and details. It evaluates all present and future costs necessary to construct, operate, and maintain systems. and it provides a long-term assessment compared to evaluating only the initial capital costs. And this is something that we often encourage end users and stakeholders to do, and that's look at cost in a long-term context. Let's not just talk about what that gravity system or vacuum system or even low pressure sewer system is going to cost up front. Let's talk about what it's going to cost over the course of a lifetime, because that's really where the cost can be found. And certainly when it comes to other types of low pressure sewer systems from competitors, that's a conversation that we always encourage folks to have, is look at cost in a long-term context before making critical decisions. And the beauty of our life cycle cost analysis service is that we can get into some pretty minute details, or we can keep it high level, kind of back of the napkin to get a conversation started. We want to look at some required data and parameters, installed capital costs, including rehab, post-inspection. Again, it can get pretty granular. What's the annual operation and maintenance costs expected to be? Post-renewal, I&I, these are all things that we're looking at. And also financial criteria. What's the cost escalation rate likely going to be? What's the discount rate? And of course, what's the project planning period that this is all going to fall within? So for anyone out there that's interested in learning more about our life cycle cost analysis and our gravity cost calculator, would encourage you to go to www.e1.com. It can be found there, or contact your local E1 distributor, or just call our factory. The analysis includes all operational parameters, cost to transport and treat I&I, post-rehab sewer inspection and cleaning, even lift station and other component costs. And again, what is that planning period? We find optimal planning period is typically between 20 and 40 years, and that's usually driven at the state or local level. So how much do these systems cost to operate? This slide here calls out two municipal E1 installations. One is Jerusalem, New York, and one is Fairfield Glade, Tennessee. As you can see, the average cost per year for Jerusalem is typically between, call it $30 and $40, or about $35 per year. With Fairfield Glade, similar, but these are third-party analysis of what the operation and maintenance cost for each system is. We have literally dozens of examples on our website and other locations of operation and maintenance costs. That's not our data. It's information that comes from the field, from the actual municipalities or engineer of record. We have noticed through the years that E1 systems can cost somewhere in the range of $20 and $30, or even lower in certain cases. And that is certainly very economical when weighed against other types of collection. So the conversation from a design standpoint really starts with the methodology that's used to design an E1 system. I want to just draw everyone's attention to the table on the right as we kind of get into this. But at Environment 1, we utilize what's called the probability method to design, not the rational method, which is most often associated with lift station design. But there are some other manufacturers, particularly of centrifugal pumps, that provide pressure sewer system that will use the rational method. One of the issues that we take with the rational method is that it calls for too many variables. So what we do is we use the probability method. The probability method is based on empirical evidence and data over the course of 50+ years of designing and installing and monitoring pressure sewer systems. It really goes back to 1969 with what's called the Albany study, where a number of grinder pumps were installed. And the theory was that only a certain amount would turn on at any given time, almost regardless of the circumstances. So the whole concept and objective behind the Albany study was to validate this theory of the probability method. But basically what it means is that at any given time, when it's sequenced out over a range of connections or pumps, only a certain amount of pumps can be expected to run at any given time, including during peak flow hours. So let's just take a look at this table. You'll see pump number 1 on the left, number of grinder pumps connected. There's pump 1, which is actually zone 1. Then it goes, let's just go up to 30, between 19 and 30. If you look to the corresponding spot on the right, we know, again, through empirical data going back 50 years, that number 5 is the amount of SIMOPS, or simultaneous operations, that would be occurring for that many connections at that given time, even in peak flow situations. So, we get questions all the time about how it is that our systems can be, so small. The diameter of our pipes can be so small when we're accommodating so many households. And I'd like to just take note that the system, if you will, is the network of pipes out in the community or out in the street. The grinder pump is the thing that makes it all happen and work. But I would just call your attention down to the bottom. You'll see in this system, there's 1,004 connections, but there's only 35 related simultaneous operations. The answer to that question is we only have to size that pipe for 35 simops typically, as opposed to all 1,004 connections. So that's the basic crux behind what we're doing. It's based on how many pumps can be expected to be running at the same time during a peak flow situation. A big driver of our business is what's called septic abatement, and it's certainly becoming more of a prevalent issue in this day and age. You know, when you pick up the newspaper, often we can read about algae blooms and groundwater pollution that's taking place, and from Long Island, New York, down to several places in Florida, and certainly even in the heartland and all points in between. This is because septic tanks have a life cycle. A lot of people don't realize it, but they do require maintenance periodically, and they are subjected to degradation over time. Odors can exist. It can lead to home site depreciation. There are safety factors associated with septic tanks and their failures. They can cause, again, pollution in groundwater, and there have been cases where private drinking wells have been contaminated, certainly in areas where you have high density and a lot of septic tanks hooked up or connected or existing in one particular location. It does pose a serious public health issue. There's a significant amount of pathogens that leach out of septic tanks when they're not functioning properly. Leaking septic tanks may be unacceptably noxious, and collapsed tanks, again, can present a physical, personal safety issue for people. So again, septic abatement is a big driver of what we do, and we certainly have numerous examples from 50 years of being in business of successful septic abatement situations where our systems have had a positive impact on quality of life. This slide shows what the system looks like when it's installed in the ground. It's kind of the ant farm view. If you can imagine kind of a slice of the ground, this is what it's indicating. So we'll just start off to the right, and we'll start up at the house itself. You'll see that there's an Environment 1 Sentry alarm panel hooked up to the side. That's an alarm panel. It's not a control panel. There's a distinct difference. We house our controls in our pump for two primary reasons. Well, number one, it's going to deliver more reliability that way because the pump is climate controlled. Heat and varying fluctuating temperatures are the enemy of electrical components. So if you have controls up in a panel and it's in a very hot climate or even a hot summer day, and even a place like the Northeast of the United States, temperatures inside that panel could get very hot. So we don't want our controls up there. We want them in the pump chamber where it's climate controlled, if you will. Also, closer proximity to the motor, or closer relationship from a distance standpoint between the motor and the controls, is a more reliable design because it reduces the potential for voltage drop and interference. Panels can be located quite a distance from the actual motor, so we want to keep those controls as close as possible. But if you go down to the bottom, you'll see that's an inlet that connects the household waste, if you will, to the wet well on this E1D series grinder pump station. And above that, not to leave it out, there's a conduit that connects the alarm panel to the station itself, and that is going to house and connect the electrical connections required for that pump system. So at E1, we need 240 volt single phase power. We need a 30 amp dedicated breaker in the house. And again, that's connected from the alarm panel to the station, typically via conduit. There you see the core in the station itself. Our stations utilize corrugated material that can be foam filled. That's a double wall design. We offer the wet well, dry well tank architecture because it increases reliability and safety and serviceability as well. There you see the pump down in the bottom of the tank, again, in the wet well. And below that, there's a ballast, and there are prepackaged ballast systems available out there. Exiting the tank on the left side, if you will, is a 1 1/4" discharge, which connects to a lateral. Usually a stainless steel unilateral in the case of E1 would be required. which is fully tested and contains an isolation valve, a flapper check valve, and a clean out port. But that usually is the demarcation point, folks, between private and public lands. And then beyond that, typically the force main is located out in the street. And again, with an E1 low pressure sewer system, force mains are typically between 2 and 4 inches. Again, with the total focus on maintaining low operation and maintenance costs, we want our systems to be easily installed. They're factory tested. We want them to be plug and play on site so that there's no human assembly, or as little human assembly required as possible. So everything is factory assembled and tested at our factory before it leaves. It comes complete with a basin, a pump core is inside that tank. It's got the check valve, which is intrinsic and included as part of the design, and the anti-siphon valve. The alarm panel would be tested before it leaves our factory. There's no assembly required of these in each individual components. The tanks themselves are field adjustable. This can be accomplished either with a 6-inch riser or a slip-on style extension, which can get you up to 3 or 4 feet. And again, that tank is double wall construction. We'll talk about it a little bit more in the coming slides, but the device off to the left is what's called an electrical quick disconnect. That's a NEMA 6P rated connection with a radial seal, and that would replace a junction box. And keep in mind, junction boxes require screwdrivers and screws, and you know, that's not exactly a user-friendly design as far as we're concerned. So we make this EQD, which is literally a plug that turns about 3/4 of one way to be locked and sealed. Again, keeping with serviceability, this core mindset versus individual components. Some of the things you're not going to notice inside of an E1 station are floats. The reason for this is because floats come in contact with wastewater. And when you have a control system that comes in contact with fats, oils, degreases, debris, and various solids, you're going to have a control system that is adversely impacted at a minimum by those things. So we house our controls, which are pressure switches, up inside the core itself, and they never come in contact with wastewater. But again, we want to streamline the inside of that basin. We want to eliminate things like floats and float trees and junction boxes and rails and things that we don't feel belongs you know, in a pressure sewer system environment. We talked about the EQD. Again, that replaces a J-box. All of the components on the inside of a D-series station that E1 manufacturers are going to be stainless steel. And again, that is to reduce the possibility of corrosion in that wastewater environment. And we talked already about alarm box versus control box and the philosophy and mindset that goes into that. Often overlooked in low pressure sewer system design is the unilateral. And I guess about 10 years ago now, maybe a little bit more, we came out with what at the time was a proprietary unilateral, because you know, over the course of, at that time, you know, 40 years in business, again, going back 10 years, we began to notice that, you know, maybe there wasn't enough attention given to the lateral, and it often consisted in practice of, you know, plastic components that were sourced from, you know, wherever, and, you know, glued and maybe not tested as adequately as they could have been or should have been, or maybe there was no lateral at all in the system. So we decided that in order to best serve the market and our customers, that we had to kind of take charge of this area, and we came up with this 316 stainless steel unilateral. It's 100% tested at our factory. So before it ends up on your job site, we're going to make sure that it holds pressure, it doesn't leak, and it does its job the way it's supposed to. Again, it's got a check valve to prevent backflow. It's got an isolation valve, which is fully ported ball valve, and a clean out port as well, in case you need to jet that line out for whatever reason. It's designed specifically for use in pressure sewer systems. And we require it. We believe so strongly in this component that we actually require it as part of our stations. So just to kind of get back to basics about the pump system itself, you know, what are the specs on these things? Well, we talked a little bit about the power requirements, 240 volt single phase. What I haven't mentioned yet is that this is a 1 horsepower, single horsepower pump. It's progressing cavity, which means it's going to produce a tremendous amount of head potentially, and you know, more importantly, it's going to be a predictable flow type situation. So we go up to 185 feet of total dynamic head, as I mentioned. This is ideal for uphill pumping. It's ideal for long distance pumping. You know, on flat ground, an E1 pump can go about 2.5 miles through the discharge line. That's very significant, provides a tremendous amount of freedom and flexibility for end users. We talked briefly about the pressure control design, and again, those switches are pressure switches. Are the same ones that are in your washing machine at home or your dishwasher. Very reliable, very simple, incredibly simple design, but they deliver years of reliable performance. We want them up inside that pump. They're activated by air column. And the benefit of that design is that it is actually interfacing with water level while never coming in direct contact with it. Everything in our design is interchangeable, and although we deliver mean time between service calls of 10 years, and that is typically for wear components, the design life of the asset is 25 plus years, and that's certainly not uncommon for an E1. This is a kind of a busy slide, but we wanted to address hydraulics in some capacity and give you folks an idea of what kind of makes us different. So I'll just start at the left side of the slide here. You'll see that there's a blue curve that's nearly vertical. That's a system curve. On the bottom, on the x-axis, you'll see if you start at the x and you work your way right, you'd have an increasing number of connections, up to about 20 in this case. But you'll see how that naturally progresses up into almost a nearly vertical curve. The demarcation point is the y-axis in the middle. And then if you go to the right, you'll see the E1 curve, which is a lighter blue curve, which kind of lives in that same zone as a typical system curve. So what does this mean to you? Well, it means that this is a pump that is going to work in an incredibly wide range of applications and conditions. This is residential low pressure sewer. These are not lift stations. You're not going to have pressures. You should not have pressures up around 80 or 90 PSI. Typically, we're going to see them even in high pressure situations at 40 or 45 PSI, somewhere in there, certainly well within our range of capabilities. But the point is, you're going to have varying pressures. This is just a snapshot in time. That system curve might look a little bit different if the flows were a little bit different. This is really an average, but you're going to want to specify and install a pump that can deal with a wide range of varying pressures. Now, conversely, if you look at the centrifugal pump curve, that is very typical for a centrifugal pump. And no one's going to sit here and say that centrifugal pumps are bad. They're great for the designed application. If you need a big lift station needs to produce 110 gallons per minute, by all means, you should absolutely be using a centrifugal pump. You shouldn't be using an E1 pump for that application. So, but by the same token, in a low pressure sewer system where you've got these adverse and diverse range of conditions that you're dealing with, you should be looking at a pump that's designed specifically for that application. So this slide points out the tremendous difference between the two pump characteristics. So a little bit of a comparison between semi-positive displacement grinder pumps and centrifugal pumps. With an SPD pump, you're going to have a stator and a rotor, and that's based on the Moigno principle. It goes back several hundred years, and really what it is a sequence of chambers that progresses and actually physically pushes water out of a discharge location, as opposed to a centrifugal, which creates a vortex and then typically would create a vortex and allow a discharge location. Metaphor for that would be with the SPD pump, it's akin as to taking your hand when you're in the pool and squeezing it and making water come out of the top of your hand. It's one of the best analogies I've been able to think of. It's actually physically pushing that water and not giving it really anywhere to go but out. With a centrifugal pump, an analogy that I learned once was if you filled a bucket with water and you tied a string to the top of it or a rope to the top of it, and you drilled a hole in the side of it and you spun it, you were strong enough to spin it around above your head. At the bottom of that, or coming out of that hole, would be a stream of water. Well, a centrifugal pump in many cases is doing something similar. Again, it can produce a lot of flow, but it can very easily be pushed back on that curve as well. SPD pumps don't spin as fast as centrifugal pumps. They typically go at 1750 RPM. That's low velocity, high torque, as opposed to a centrifugal pump, which is going to go operate at a high velocity and return low torque. We really put a lot of emphasis in this aspect of the design. You can see a lot of videos on YouTube showing pumps chopping up a pair of jeans in 3 seconds. If you saw an E1 grinder pump demo, you would notice that it would steadily and slowly take kind of little nibbles out of solids and grind it up and pass it along. That equates to more reliability. That's a design that's not going to get jammed up as easily because, again, it's more like a grist mill. It's operating at a low speed with a lot of power, a lot of torque behind it. Our grinder also does not require sharpness to do its job. A lot of the cutters out there on centrifugal pumps need to maintain sharpness in order to work. And that's certainly not the case with our system. Again, we talked about the internal controls versus floats, and we try to simplify every aspect of that design. We want the inside of that station to be as streamlined and clean and simple as possible because that relates to less cost. Centrifugal pumps use dielectric motor oil typically. The motors are in an oil bath to maintain temperature control, if you will. A lot of times folks overlook this aspect. Wherever you have oil used in this context, you have a potential liability. It's got to be documented. It's got to be dealt with. Again, our pumps are serviceable. If there's an issue with the motor on any one pump, it can be fixed on site. The asset can be returned to service. If you have a bad motor on a centrifugal pump, typically you're not going to drain the oil out of it on the back of the truck and replace it. You're going to push it and pull it conceivably without doing any troubleshooting diagnostics. And, who knows if you're ever going to get to the root cause of the problem. So oil-filled motors, we avoid that through our air-filled motor, which is pressed into a casting, if you will, which is located in the wet well of the station and efficiently dissipates heat. With centrifugal pumps, you've got a small 2.5-inch inlet, which is prone to building up solids. And again, if it's a cutter that requires sharpness, which it would in the case of a centrifugal pump, you're going to have frequent jamming. Floats, we've talked about them pretty extensively. J-boxes we've mentioned as well. Their separate pump level and motor controls make service more complicated and time-consuming, and they may require larger horsepower pumps to overcome varying head conditions. At E1, we have the upgrade program where we replace competitor units and systems throughout the United States and the world. We have seen instances where there have been 5 and 7.5 and 10 horsepower pumps hooked up to a residential application just to overcome force main pressure, and documented cases in those cases where we have been able to go in with our little single horsepower progressing cavity pump and operate with no issues whatsoever. This slide shows a sort of a comparison between the cutter wheels. In our case, it's a grinder. The other guys use the cutter, which requires sharpness. The inlet velocities become very, very critical when you're kind of analyzing these designs. When you're looking at any one grind demo, you've got an inlet velocity going into the wet end of that pump at about 4 feet per second on the high side. If you compare that with a centrifugal pump, which can have inlet velocities of 22.8 or 23 feet per second, that is a tremendous amount of velocity. So now with the centrifugal design, you have a cutter that requires sharpness, you have that high RPM, and you've got that intense velocity going into the bottom of that unit. It can be a recipe for frequent jamming. The other thing I'd like to mention is there's 2 paddles on the E1 cutter wheel, if you will, and those are there to create turbulence inside of the tank. One of the things that we noticed over the years is a lot of municipalities that were using centrifugal pumps would budget for these preventative maintenance campaigns where once a year, maybe twice a year, they go out and they pump out all their stations. Again, this is not E1. This would be a different provider to get all the solids out of the tank throughout the system. And there's a tremendous amount of cost involved with that. Well, with E1, you don't have to do that because there's so much turbulence inside that tank that solids are suspended and they're passed through the system, and they're not accumulating in the bottom of the tank over time, causing issues. So that is something that I wish to call everyone's attention to. Again, we make an alarm panel, not a control panel, and we get into a lot of features and benefits. We have in some places in the United States, our standard offering is a Protect Plus panel, which is going to protect the asset from a wide range of potentially troublesome conditions, including brownouts, low voltage, kind of the same thing, inadequate power, overpressure conditions, really protects the asset from a wide range of conditions. And these have liquid crystal displays on the front, which allow a service technician to go in and actually access alarm history so that we can figure out if there's any type of issue, what it might be. Again, the focus is on keeping operation and maintenance costs as low as possible. So this panel was really designed to assist in that process by making troubleshooting more efficient and effective, not only by protecting the asset, but by documenting alarm situations. As far as telemetry goes, monitoring and protecting the asset is really becoming more and more important to design engineers and various stakeholders throughout the industry. We make what's called an advisor system, which is a cellular-based system that is housed inside of the panel itself. What this is going to do is it's going to determine when there's an alarm condition, and it's going to communicate that that condition to the responsible service entity. So a lot of times what happens with these systems is it makes that alarm notification completely seamless, and the responding service technician can arrive on site and deal with an issue often before the homeowner even knows there's a problem. So we're with this advisor system, which is very cost effective, not only from an initial cost standpoint, but from an ongoing data standpoint. We're really making the asset, we're achieving that highest level of reliability by catching alarm conditions and potential issues in the beginning, if you will, rather before they progress into more significant issues. And again, a lot of times we can respond to a service condition even before the homeowner knows there's an issue. Product validation testing is really very important to what we do at E1. We have at our facility, which is an ISO 9001 certified facility and engineering lab, where ongoing destructive testing takes place, where we're literally just trying to break pumps as much as we can and learn by that process. We have the ability to run the equivalent of a neighborhood with 34 homes in it at any given time. And what we're doing is we're continually testing these units by following certain protocols, which we'll get to in a couple minutes here. But again, trying to learn from product validation testing to make the asset as reliable as possible. Continuous improvement is really front and center with everything that we do. We're focused like a laser on this unit, and again, we want to make it as reliable as possible. One of the protocols that we're held to is NSF third-party testing. This standard is 46-1997. To our knowledge, at this moment in time, we're the only residential grinder pump manufacturer that adheres to this or achieves this. But you can see that it calls out a specific item to be entered into the station with a specific frequency. This is a random test. Some of these items, for example, toilet tissue or facial tissue, egg, paper towels, so on and so forth, all the way down to metal toy cars, which are matchbox cars, wooden pencils, toothbrushes, things like that. You'll see on the right the frequency that those have to be added. And basically what this test it gets down to is whether or not our pump can deal with all of these things without jamming, which it certainly does. So with that being said, I want to thank you once again. I hope there's some questions here at the end of our presentation that I can answer for anyone who's interested. Rachel?
Chris, thanks for that excellent presentation. So as promised, we'll start right in on our Q&A session. Chris, you ready?
I am ready.
Okay. What happens when the power goes out?
Well, when the power goes out, if it's a unit with a generator receptacle, you can still run the unit without any issues. We give you a couple days worth of storage in the tank itself. I would like to make note of the fact that when the power goes out, household water usage is decreased very significantly. You're not doing things like laundry, and you're not maybe taking showers with the greatest frequency. So we give you a couple days worth of storage in that tank. And, we have numerous examples of power outages occurring for several days in some cases with relatively few problems. I would make mention to the fact that down in the Florida Keys, when Hurricane Sandy came through, there was existing gravity infrastructure and a low pressure sewer system. And in some cases, they discovered, in actually most cases, that the low pressure sewer system could be restored much quicker than the gravity system as well. And the way that occurs is literally as they were restoring electrical power, they were simultaneously restoring sewer. So we give you several days worth of storage, and it can be pumped out with a generator as well.
Okay, thanks. I was hoping you could describe some unusual uses you have encountered, such as conveying only liquids, gray water or urine, or only solids.
Well, my answer to that would be that the pump is designed to deal with normal household waste water. It's not designed for anything extravagant from a process and treatment standpoint. That being said, I will tell you that there are numerous examples of kind of out in the marketplace. Various engineers and end users have used the unit to pump effluent in certain situations where you can submerge the pump fully. However, that's not recommended. If you were to call our engineering folks, they would encourage you to use the pump for what it's designed for. Again, normal household waste or light commercial use. As far as more on the solids end of things, we have learned of these pumps being used in sort of dosing applications or kind of as metering pumps inside of wastewater treatment plants. Again, being an SPD pump, the flow rate is so predictable that some engineers like to use them for that. But the pump's made to deal with light commercial and residential.
Okay, thanks for that. This question's just come in. Where on my property would I install the pump?
Well, the short answer is anywhere you want, typically, as long as it makes sense with your existing plumbing infrastructure and it's in line with your personal preferences. So typically the pump is located where it could be easily serviced. That's usually up by the street or where there's a right of way. I will tell you that oftentimes homeowners and designers like to tuck these things away where they can't be seen. Maybe it's behind a bush someplace. But the beauty of low pressure sewer is that it offers so much flexibility that, strictly speaking, you could probably get that pump to work in almost any sense. Keep in mind, the further away you get from the house, the longer your run on your pitch or your incoming inlet is going to be, and the deeper that tank has to be to hook up. So that comes into play as well. But I would say with municipal projects where it's a septic abatement type situation, more times than not, they're up closer to the road where the service crews can come and respond and spend as little time as possible on private lands and get out and access the station obviously easier. But if aesthetics is very important to you, you can literally put it almost anywhere you'd like.
Okay, we're looking at a septic to sewer application. What is the main advantage of pressure sewer versus vacuum, for instance?
Sure. Well, certainly the initial cost to install the system is going to come into play, and we have more information to back this up, which I'll be happy to provide offline. But ongoing operation and maintenance costs with E1 systems are significantly lower. Reliability becomes a very big factor in this as well. I mentioned earlier in the presentation that E1 low pressure sewer does not require a centralized piece of infrastructure to work. Vacuum systems are built entirely around centralized infrastructure. So if you have a problem out in the system, let's say it's a leak, you are going to have an entire community potentially without sewer. If you have a problem with a grinder pump, you have a service call on one house, and the people that live next door don't even know about it. So that would be a couple things. Also, electrical costs associated with running vacuum stations are astronomically high. Whereas with E1 utilizes the equivalent energy of a 40-watt light bulb, probably for less than 10 minutes a day, typically. So it's going to provide a little bit of CapEx reduction up front, way more reliability on the back end, and the lowest operation and maintenance costs available when you compare gravity, vacuum, and pressure sewer.
Yeah. Okay, in the pipe systems, is it required is a check valve required in every joint, or is it enough with the lateral kit valves?
We don't recommend check valves out in the system. If that system is designed in accordance with our recommendations, it's going to achieve the required velocities, and there shouldn't be any issues out in the system. That conversation starts on property with the grinder itself. anything that's going to go into that system is going to be a fine slurry. If it's an E1 and you're not going to have solids up there, there really isn't a need for check valves out in the system. Isolation valves, potentially, and flushing connections are what we see the most of, but the flow is directional. You're not going to have any issues with backflow in a pressure sewer system under normal conditions. So that's not something that we recommend. The lateral itself, there's a degree of redundancy with our system because we've got a backflow preventer on the pump in the station, and we've got it up at the check valve with the unilateral. So we feel like that's, and we know that's a very reliable methodology.
Okay, so now we have some alarm panel questions for you. Is there a way to selectively program the alarm activation with the lamp only, where nearby rooms could experience noise discomfort at night?
Initially, I wouldn't recommend that. We wouldn't recommend that at E1. That alarm is there to notify folks when there's an issue. So we want the end user to understand when there is a condition where a service entity needs to come up and address a potential problem. I've had this question before over the years, and my answer is don't do it. leave the alarm as is, and let's know about potential issues when they occur so that we can address them in a timely and safe fashion.
Yes, absolutely. So does the cellular alarm require an ongoing expense?
It does. There's an ongoing data expense, roughly equivalent of a can of soda per week. So, couple dollars a month, that kind of thing.
Okay. And can your units be installed in the basement?
They certainly can. And we see that quite frequently in areas of the country where basements are prevalent. A lot of advantages associated with that. We make an IDU unit, which gives you 90 gallons of storage, and is an aesthetic unit that's designed to be in a utility closet or in a basement, as mentioned. They can sit on the floor, or they can be actually installed what's called inside the slab, or basically flush to the ground, with the exception of the cover. So yes, we can do that. It's going to save you some money on installation because you're limiting excavation outside the foundation. Some engineers prefer for that functionality to be outside, instead of inside the house. But the indoor units that we offer, which are not just limited to the IDU, there's a variety of different stations that we offer that can be used indoors. But they do offer a wide range of flexibility and benefits.
So besides residential and municipal use, Chris, what other non-typical systems have you seen this system work well in? So I think this person is referring to non-residential applications, but
light commercial is a big part of what we do. We want to have an understanding of what that application is, and part of it, what makes us different is, if you're the caller factor, we're going to want to learn about what you have going on so that we can provide the best possible solution, rather than just, hey, buy this station, because it's the easy thing to do. We say no a lot. And we take pride in that we're always going to do what's right by the customer. But to get to the question, the diversity of application is tremendous. Everything from strip malls to actual shopping malls, restaurants we see a lot of, hotels we see a lot of. Our units go up to 2, 3, and 4 pumps per station. So we see a lot of multi-unit residential housing. We see warehouses that are utilized. So in terms of non-typical, commercial, light to medium commercial is what we serve. And, I mentioned some of the other stuff earlier in the presentation that, we have learned about over the years, but, the diversity of the applications that this system can be used for is, more times than not, as long as the flows are appropriate and the incoming type of flow is appropriate, we're going to be able to give you a really cost-effective solution.
And this question just in, what is the difference between the D series and the W series stations?
The D series is a wet well, dry well system. So if you can imagine opening up the top of the tank and looking in, you'd see a safe, dry pit instead of the wet well itself. D series has stainless steel internal discharge components. It has a ball valve, fully ported ball valve, but the core itself has a top housing, and there's a clear demarcation. The architecture of that tank is clearly separated into two factions, the top being that dry well and the bottom being the wet well where the wastewater goes. So the benefits are serviceability, safety, and it's really goes back to the original design, the original intent of the product itself, going all the way back to 1969. With the wet well, it's an open wet well. Some people will say it'll give you a little bit more storage, but that depends on your definition of storage. But really, we're using that W series product where we're in markets that require a certain price point and or maybe based on certain preferences. Some municipalities like to see inside the tank when they open up the cover. So we do provide that option for folks that are a little bit more comfortable with that open architecture. But up in the Northeast and, I'd say most places up this way in other areas of the country, we see mostly D series units.
Okay, I'm gonna do a little combo effort here on two questions for you. So the first one is, how do you determine zone size? For example, number of pumps, geographic area, et cetera. And so this is just kind of a follow-up one. It seems pipe sizing is important due to variable flow rates at different times of the day. What method do you recommend?
So the first question is, I may ask you to go back to that second one, Rach, but the first question is, what designates a zone is every time we have an increase in simultaneous operations of one. So you're going to get an increase in SIMOPS, and when that happens, we're going to add a zone to the system. Again, somewhat counterintuitive for some engineers because there's no formula, if you will, behind it. It's all based on empirical data, going back 50 years. But we know how many pumps typically are going to run with a certain amount of connections. So where those SIMOPS increase by one, we're going to add a zone. But keep in mind that as we do that, the sequence of pumps can increase, or the sample of each zone can increase. And that is something that I think is best answered in kind of in a one-on-one context where we can flesh out individual questions about a certain application and kind of walk this person through it. But the thing that determines increasing in zones, an increase in zones, is where we know we're going to have an increase in simultaneous operations. The second part.
Okay, so the second part was, it seems pipe sizing is important due to variable flow rates at different times of the day. And certainly in this day and age, when we have stay-at-home orders and so forth, which method do you recommend?
Well, it starts with the daily flow rate that we use per EDU, which is typically at environment 1 is going to be 200 gallons per day. We use peak factors, and that is driven, I think, in large part by what they're asking for locally. Usually between 4 and 5, sometimes 6 hour peak flow. So we're gonna compact or condense all that flow into a peak flow period, and kind of throw all the flow we can at that unit to make sure that the unit is applicable and appropriate for the application, but B, to make sure that our line sizing is appropriate. There can be significantly higher flows during peak flow situations. The beautiful thing about the probability method is that it's incredibly forgiving, and what we find is that over time, again, having done this for 5+ decades now, that it is a great way to design systems, and there have been relatively few issues in 50+ years that we're aware of where someone had designed something inadequately. If you're following our protocols, we're going to understand what those peak flows are, what they should be, and we're going to make sure those lines are sized appropriately so there's adequate velocity. And let's not forget, we don't want to oversize them either, so there's too much retention, which can lead to things like septicity and odor problems. So we optimize those pipe systems, and we kind of choke them down, get them just to the right point to where they're producing enough velocity and they're not experiencing excessive retention.
Okay, and I think we have just a few seconds left. Do the pumps typically belong to the utility or the homeowner?
I'd say it's 50-50, depending on the era, if you will. Once upon a time, there were a lot more municipal, projects available out there, so if this was 15 years ago, I would have said municipal, but it's 50-50, and that's another beautiful helpful aspect or valuable aspect of a pressure sewer is the fact that if the utility wants to be in control of these, they can be. We'll provide all the training they need. We'll make sure that they know how to go out there and deal with the system on a daily basis. Or if the homeowner, it's determined that they would be the best entity for that particular community to be responsible for them. Again, it's an appliance. It doesn't cost a lot of money to operate or fix. And the service rate is very infrequent. A lot of times kind of a hybrid of those two are HOAs or homeowners associations. We deal with a lot of those as well. We can tailor an ownership model and make recommendations for almost any scenario that anyone can think of from an ownership and maintenance standpoint.
Good. Okay. Well, it looks like we're just about out of time here, Chris. Thank you again. And I must say you all were excellent attendees. You asked a lot of great questions. We had several, and I mean several, that we didn't get to. So look for our follow-up email that will include answers to all the Q&A. On behalf of all of us at E1, we thank you for joining today's session, and we look forward to seeing you soon. Be well.